So today we are going to start with the first topic, that is rectilinear motion. So as I said earlier, rectilinear motion meaning the motion in a single dimension. So that means any particle traveling in a straight line is called a rectilinear motion. So that traveling in the straight line meaning it may be in the positive direction of the x or it may be on the negative direction of the x, but still we say that it is traveling in a straight line. That means suppose if you take our normal coordinate system like this, a two-dimensional coordinate system. So this is y-axis and this is x-axis. Now on this x-axis actually we are identifying a particle which is traveling. That means this particle will be traveling only along the x-axis, maybe in this direction or maybe in this particular direction, right? So that means the velocity or the acceleration or the displacement, right? So it is always a function of x only. That means, so the velocity and the acceleration is a function of x and x equal to x is anyway x. So this x is indirectly a function of t. So these are the mathematical relations actually we are going to deal with in case of rectilinear motion. So that means we are not worrying about this y-axis at all. So that is the beauty of this rectilinear motion. So this is pretty simpler aspect, right? So here in the rectilinear motion, so what we deal with is first we need to identify what is displacement. So in the entire dynamics, what we are going to deal is only very few different variables. Those variables are, one is the displacement, another is the velocity, and another is acceleration, and the fourth one is the time. So whatever may be the complex level of problems we are going to solve, we are always playing with only these variables. So as a substitute to this, the cause of all these things is the force. So except for these aspects, we are not going to deal anything, right? So this is the scope of the dynamics topic completely. Now here, the relations between these things actually we will be establishing for different types of motion, maybe in a one-dimensional motion or maybe in a two-dimensional motion or maybe in a three-dimensional motion. So to be specific, in rectilinear motion, we are worrying about a particle which is traveling in one-dimensional motion related to all these variables. So here, what is displacement? So displacement we mean if a particle is displaced from point A to point B, that means the place of the point is changed from one location to another location. Suppose if there is a car that is traveling from here to here, so when I look at it the first time, so this is at the point A. Now actually after some time, if I notice the car is traveled to point B, that means I notice that the car is traveling from point A to point B within a time of t. So now here there is an associated direction from point A to point B. So if there is an associated direction, definitely we will call that as the vector. So this is displacement is nothing but a vector, and this is replaced with a single variable called x. Now this x displacement that happened from point A to point B within a time of t. That means x should be a function of time. X should be a function of time. So this x and t are interrelated to each other with respect to the displacement from point A to point B, right? So here actually the car can travel in this direction also, but here from point A to point B we treat that as that displacement, this one, but this is what we call as the distance. But actually in case of three-dimensional or two-dimensional motion, so though we are traveling from point A to point B in the top path, still we treat that as the displacement vector with a condition that, so from here to here it is moved as if it is like a vector, and from here to here actually it is moved as if like it is a vector, and from here to here it is traveled as if like it's a vector. That means the displacement is continuously changing with a minute vectors identified as a tangent to that particular path at every location. That means displacement still be a vector though it is traveled in this particular direction. But if you take as a gross look from point A to point B, this is what we treat as the distance, and this is what we treat as displacement. But we are very specific to application of the calculus, hence we should be taking the changes that are happening in both the time and the displacement of very minute in nature. That means limit delta x delta t tending to 0 x. So this is what actually we are going to calculate, where this is delta x by delta t, and this is what we treat as dx by dt to calculate the velocity. Here if you notice, this delta t is tending to 0. Tending to 0 meaning almost 0 change. When there is almost a 0 change, that means the displacement is almost like a 0 value. That means every point to point change we treat as a displacement vector. So from here to here, when it is traveling at any point of the time, actually if you calculate the dx by dt, which is nothing but the slope of the tangent drawn in this particular direction. Now here, this is the instantaneous velocity at this location at any time of t. So at t, if you calculate, this is the instantaneous velocity. This is the instantaneous velocity. But actually as a whole, if you treat it, for example, suppose if I am traveling from one location, let us say from Hyderabad to Bangalore, I am traveling. Now actually when I start my car, so I might be having certain velocity and certain direction. Now actually, maybe after 10 hours or 15 hours, right? So I might have traveled to Bangalore directly. Now actually, the person actually, whoever wanted to count the velocity that he has taken, or the displacement total, he traveled from point A to point B. So this is Hyderabad and this is Bangalore. Now actually I might have taken different routes. Finally, I reached to this particular location. Now at any instant, if I take it, my velocity may be different at that particular time. So I might have started with 10 kilometers per hour, but when the road is very smooth, I might have traveled with maybe 100 kilometers per hour. But if there is a hurdle, then actually I might have stopped there itself with 0 velocity. That means all these aspects actually happen from point A to point B. So from Hyderabad to Bangalore, actually when we are traveling, there are multiple velocities I have taken. But as a whole, if you notice, so when I say that actually I have taken 15 hours to travel from Hyderabad to Bangalore, then immediately the way we do is we calculate manually what is the displacement between these two. That means what is the distance between these two, and then what is the time I have taken on total from Hyderabad to Bangalore. So I don't count about all these directional changes or all these velocities. So here total displacement is nothing but x, and total time I have taken is t. So then actually I calculate x by t, which we call as the average velocity. Now if you notice, total displacement and total time I have considered there. But at any instant, if I notice, the velocity will be different, because there whatever, so within that particular fraction of the second, I might have traveled 100 meters within 1 second. So 100 meters within 1 second is nothing but 100 meters per second is my velocity there. So that is what is the instantaneous velocity. But on total, if you count from here to here, we treat that as the average velocity. So these are the two different kinds of velocities in the problem statement actually that usually will be given, right? So here, so this is the displacement. Now the velocity is nothing but the rate of change of displacement. So when we are traveling, so every time actually we are keep on changing the velocity, or we might travel with a constant velocity. So depending upon that scenario, there will be a rate of change of displacement, and that rate of change of displacement is called the velocity. So this is related to dx by dt. Now the acceleration is nothing but changing the velocity continuously. So if you change the velocity, so that change is treated as the acceleration. Now the change can be positive direction or the negative direction, which essentially means that, so I started with 10 kilometers per hour, and then actually within next second actually I traveled with a velocity of 20 kilometers per hour. That means I have changed the velocity from 10 kilometers per hour to 20 kilometers per hour within 1 second. And that's what is my acceleration. That is 20 minus 10 divided by within 1 second. So this is the 10 meters or kilometers per hour square. So this is 10 kilometers per hour square is the acceleration with which I am raising my speed. Suppose actually if I reduce the velocity from, let us say, 50 kilometers per hour to 40 kilometers per hour within 1 second, that means I have reduced the velocity, which we treat as the negative acceleration. So negative acceleration is also called as the retardation. So negative acceleration is called as the retardation. So here displacement change implies velocity and velocity change implies acceleration, but all are as a function of time. So within time, so this is the fundamental variable we treat, x. X is a function of time, and as velocity is a function of x, so then obviously it has to be a function of time because x is a function of time, and acceleration is a function of velocity, and velocity is indirectly a function of x, and x is a function of t. So all are actually interrelated with this fundamental variable t. Got it? So here actually finally we stop at acceleration. So we don't change the acceleration again because actually that will be much more complicated but of no use. But why we stopped at acceleration is we have got this acceleration from the relation of the force. So force is nothing but mass into acceleration. So because of this reason, we stop at acceleration. We don't count change in acceleration with respect to time, right? So we stop at this location because Newton's second law says that, so the force is nothing but the rate of change of momentum, and that implies it gives a relation mass into acceleration, right? First you note down this, we are going to bring this relation, and from there actually we'll proceed. So as per Newton's second law, so force is equal to rate of change of displacement, rate of change of momentum. So this is rate of change of momentum. So momentum is defined as mass into velocity. So momentum is nothing but the effective force that when we hit. So that is momentum P. This is the usual symbol that is going to be used for momentum. This is equal to mass into velocity. Now rate of change of momentum, that means if there is a block of mass here, now on this block of mass, if you want to apply the force to move this particular block when it is having a mass of m, then initially this velocity, let us say it is already traveling with a velocity of u, let us say, and then you wanted to increase the velocity of this mass, so to a velocity of v. Now this is raised from u to v, then there is a change in the velocity. That means the initial momentum is m into u is the initial momentum, and m into v is the final momentum. Now this change happened within a time of delta t. So change happened within a time from t1 to t2. Then obviously the force is nothing but the rate of change of momentum. So F is equal to P final minus P initial divided by T2 minus T1. So this is the force. Now here actually if you replace these values, this is going to be mass into velocity minus mass into initial velocity divided by T2 minus T1. So this is mass times of change in velocity by change in time, and this is what we treat as the acceleration, because rate of change of velocity we call as the acceleration. Hence, got it? So hence actually mass into acceleration will straight away give the force for us. Now this acceleration is directly related to force. Now the force causes the acceleration causes the change in the velocity causes the displacement change, and all these things are happening within a time. So this is how actually all are interrelated. Now it is up to us, so how to treat this, whether it is on a single dimension or a two dimension or three dimension. So the change that is happened maybe in one direction, maybe in two directions, maybe in three dimensions. That means the acceleration can be in any three directions. For example, suppose the acceleration direction is this one, or the velocity direction is this one, or the displacement direction is this one. So this is a single dimension. Now, suppose actually the acceleration direction is a two-dimensional, let us say. That means it is like this, like a projectile. That means there will be a change in the velocity in the horizontal direction and there will be a change in the velocity in the vertical direction as well. That means in both the directions together, the changes are happening at one instant. That is caused by the acceleration. That means that depends on the force in which direction this force is acting on the body. So, depending on that, there will be a change in the velocity in one direction or two dimension or maybe in three dimensions. Suppose actually this is a spatial motion. Then actually in the x direction, in the y direction and the z direction, all the three different directions, there will be an associated change in the velocities because of a single force which is acting in the space. So, because of that, the motion can be in any dimension. But to be specific, we are dealing now with the single dimension. So, that means the same analogy, whatever we are going to adapt in case of one dimension, the same analogy you can even adapt, even in two dimension or three dimension, right? So, there won't be any change at all. So, that's why you try to understand these concepts clearly. So, nothing more than that. This is very, very simple topic. We are dealing with only 4 different variables and with 2 different differential equations. That's all. Got it? So, you can note down this, the relation from where actually we are arriving at all these things. Got it? So, we finally concluded that. So, velocity is equal to dx by dt and acceleration is equal to dv by dt. But actually, so this dv by dt we can even apply. So, d by dt of dx by dt. Right? So, d by dt of dx by dt. So, what I will do is, I will make d by dx into dx by dt into dx by dt. So, this is as per the chain rule. See this dt I kept at this point and then actually I have introduced a dx here and I have introduced a dx at the top. So, this way I can achieve that this can be treated as dx by dt equal to velocity. Now, velocity times of d by dx of this velocity again. So, acceleration even be treated as v dv by dx or d square x by dt square. So, as and when required, so we will be using these relations. v dv by dx or d square x by dt square is nothing but the acceleration. So, this actually from the differentiation chain rule actually we brought it. That's it. Got it? v into dv by dx is also the acceleration. D square x by dt square is also the acceleration, or d by dt of dx by dt. So, this is also the acceleration. Got it? Here actually only thing is the variable actually we are taking the derivative with respect to x by introducing a velocity here. So, dv by dx we eliminated t and introduced x. So, if velocity is a function of x, then actually still you will be able to calculate the acceleration because the acceleration says that dv by dt, but actually here if you notice x is a function of time and v is a function of time. Now v is equal to f of x is the relation where t is the parameter. So hence to eliminate the parameter and straight away get the relation of acceleration, a can be treated as v into d by dx of f of x, still be the acceleration for this. Got it? So if it is given in the parametric form, then actually we will be using this format of the equation to calculate the acceleration. So these are the fundamental relations actually what we have. So what we are going to use down the line. Now actually, so as I said earlier, if this is the acceleration d square x by dt square, there are 3 different scenarios actually what we are going to deal with. One is this acceleration may be 0, which implies that constant velocity. This may be constant. So this is constant acceleration. So this constant velocity is also called as uniform velocity. This is constant acceleration or uniform acceleration. So this is the uniform acceleration and it may be a function of time also. So this is variable acceleration. And here if you notice, this acceleration, though it is a constant, right? So this is always a vector. So as I said earlier, so F is equal to ma. So F is equal to ma, where F is a vector and m being the scalar, a is the vector, and F and a are on the same direction always, because this is a scalar multiplication with any vector will not change its direction. So F direction and a direction are the one and the same. That means, which essentially means that if I try to push this board like this, then actually this board will move in the direction of my hand only. It won't come in the opposite direction, because actually I have applied the force to change the velocity of this board in this direction. Got it? That means, so whatever the force direction it is, the acceleration direction also will be the same. So don't get confused. This relation we are going to use rigorously in case of circular motion. So there actually the acceleration direction and force direction actually we will be treating as it is. So we treat as same just because of this fundamental relation. Got it? So this may be a function of time also. So this is a three-dimensional vector also. So this vector, now actually we are treating as a single dimensional vector, because we are treating only the rectilinear motion. So in the rectilinear motion, the way we use is, so this is the x direction. Now if the particle is moving in the positive direction of the x, the velocity is treated as dx by dt. Or if the particle is moving in the negative direction of the x, then we treat this as minus of dx by dt. So this is the negative direction. So the direction of the displacement is treated as the positive. So in the opposite direction or the decreasing direction of the displacement, we treat as the negative direction. So this is the positive direction and this is the negative direction. So in the vector form, if you want to express it, so x can be treated as, x vector is nothing but xi. Xi is the vector. Now the velocity vector, actually we can treat that as velocity is equal to, so I is a constant vector and dx by dt is the velocity vector. That means whatever the direction of the x is nothing but the velocity of the velocity direction also. Now if you again do the derivative, then actually this is again I into d square x by dt square. Now if you notice, even the acceleration direction also will be on the x direction itself. So if the acceleration direction is on the x direction itself, then actually the force direction is also on the x direction. Now actually all the directions are only in one dimension. Everything is in the direction of the x. Hence it is a rectilinear motion. Got it? So this is the complete theoretical discussion what we have to be aware of to solve the problems on this rectilinear motion. Hope you have got a fair clarity on this. If you have any questions, you can let me know now. Any questions? Got it? Okay. So based on this understanding, we will solve some problems based on this. We'll start with a simple one. If at time t, the displacement x of a particle, if at time t, the displacement x of a particle moving away, x of a particle moving away from the origin is given by x is equal to a sin t plus b cos t. X is equal to a sin t plus b cos t. Find the velocity and acceleration of the particle. Find the velocity and acceleration of the particle. Can you try to find it out? Are you done? Okay. So let me solve this. See this, x is equal to a sin t plus b cos t. So if I take the derivative of it, dx by dt is nothing but the velocity. So this velocity is equal to, so even though I am not mentioning velocity as a vector, still actually it is a vector, but it is a one-dimensional vector. Hence actually even if I ignore the vector direction, it won't make any difference. So that is the understand. Though I put straight away without doing this vector. Got it? So this is dx by dt is equal to a into derivative of sin t is cos t, and so derivative of cos is minus sin t. Here again if you take the derivative of it, this acceleration is equal to d square x by dt square is equal to minus a sin t minus b cos t. Now here if you notice, this is minus of a sin t plus b cos t. So this is the acceleration. So this acceleration d square x by dt square is equal to minus of whatever it is there here is nothing but the x value. So this is minus of x. So yesterday actually I have given an important analogy. So any differential equation of this particular form, x represents the simple harmonic motion. Now actually I will show you how it is going to be. See this x value, if you notice, x is equal to, if I multiply with a square plus b square under root on top and bottom, so this can be treated as a by square root of a square plus b square into sin t plus b by a square plus b square under root into cos t. Now here x is equal to a square plus b square under root, and then so this a by square root of a square plus b square I will represent in a triangle. Now I call this angle as theta. So then actually I call this as a and I call this as b. Then obviously being this is the right angle triangle, so this is a square plus b square under root. Now here, so a by square root of a square plus b square I can treat as theta, so cos theta. So this is square root of a square plus b square into sin t cos theta plus, and b by square root of a square plus b square I can treat as sin theta. So this is cos t sin theta. So this x actually I can represent as a square plus b square under root, and then sin a cos b plus cos a sin b is sin a plus b, sin of t plus theta, where theta is a constant. Theta is a constant given by theta is equal to tan inverse of b by a. So this is theta is equal to tan theta is equal to b by a. So theta can be treated as tan inverse of b by a. Now finally we came to a conclusion that this x is varying as if like it is a with an amplitude of square root of a square plus b square. It is varying as a sin of t. With respect to time, it will be a sin theta. The maximum and minimum value of the sine function is plus or minus 1. Now if you multiply with the square root of plus a square plus b square, then the sin theta is varying from top to bottom with the limits of, this is a square plus b square under root, and at the bottom side also square root of a square plus b square, but with a negative sign. So within these two, now actually it starts with an angle of theta. So that is, so like this actually, this is keep on varying. That means this amplitude at any instant, if you notice, it is going with respect to a reference point. From the middle point, there will be a positive displacement and there will be a negative displacement. So the displacement with respect to time. So this is the time axis and this is the x axis. Now x and time axis, if you notice, the displacement values keep on increasing and coming back to 0 and decreasing in the negative direction, reaching a maximum value in the negative direction, again coming to 0 and increasing in the positive direction. Within these two limits actually it is binding and then actually moving as if like it is the top to bottom, keep on like this, it is moving, which essentially means that what is happening is, suppose actually if there is a spring like this, and this actually if there is a mass with respect to this central point, so there will be a displacement like this and there will be a displacement like this. Within this actually it is trying to oscillate forward and backward like this. This oscillation is represented as a sine wave like this. That means it can't go beyond the top limit of this a square plus b square under root, or it can't go below the down of square, minus of square root of a square plus b square. So within these limits actually it is bounded, but it is keep on moving top and bottom like this. So it's not stopping. So it's keep on moving right and left like this. So this kind of motion, it is as if like it is a sinusoidal representation for a xt graph. So this is what is the simple harmonic motion we call, and that's what is coming from x is equal to a sin t plus b cos t. If you notice, when we solve the differential equations in ordinary differential equations, so this kind of solution will be given for this kind of differential equation always. Got it? So this is actually formation of the differential equation. Actually we will solve for this. So formation of this differential equation comes to this one. The solution of this one comes to this one. So this actually represents the simple harmonic motion. So the same thing whatever you have learned in ordinary differential equation is going to reuse here without having any change. Got it? Okay, so you can note down this. Note down one more. A point moves in a straight line so that its distance s from a fixed point, so that its distance s from a fixed point at any time t is proportional to t power n. Is proportional to t power n. If v be the velocity and f the acceleration at any time t, and f the acceleration at any time t so that v square is equal to nfs divided by n minus 1. Now actually in dynamics, right, so many people actually tries to confuse between the formulas what they have learned versus the methodology. Now here actually the methodology what we are following, or actually whatever I have explained in today's class or yesterday's class, this is a standard methodology. If you go in this manner, actually there is no possibility of making mistakes. But actually suppose some people actually this acceleration, so f actually tend to treat as constant, but it's not. So if the acceleration is constant actually, then actually we have derived the formulas, that is v is equal to u plus at and s is equal to ut plus half at square. Now these are actually with an assumption of f is constant, but it may or it may not be. Suppose actually in reality in our practical life, right, so we never find this acceleration as a constant value. See, when we start the bike, right, we keep on raising the acceleration, right? We are keep on changing. That means this change is also actually continuously it will be a variable. So within 1 second, I'm going to change from 10 kilometers per hour to 20 kilometers per hour. But if in very next second, I change the velocity from 20 to 40, not 30. That means the acceleration is also changing with respect to time. Now that acceleration we call that as the instantaneous acceleration. But all these formulas are derived with an assumption of the constant acceleration. That is, these are the solutions of d square x by dt square equal to f, which is a constant. So don't try to use the formulas. Go with the normal procedure of our calculus. So here, whatever he has given the acceleration, so that is an instantaneous acceleration. So this is the instantaneous acceleration. So instantaneous acceleration is nothing but d square x by dt square is nothing but f, which is a function of t. So that is the difference. It's not a constant. Got it? So with that assumption, he said that, so this relation v square is equal to n times of fs by n minus 1 when the velocity is proportional to the nth power of t. Got it? Sorry, the displacement is proportional to the nth power of t. So a point moves in a straight line so that its distance s from a fixed point at any time t is proportional to t power n. If v be the velocity and f be the acceleration at any time. So this statement says that it is the instantaneous velocity and instantaneous acceleration. Got it? So now actually you can solve this. Also done. So this is actually manipulating the equations, nothing more than that. So what he said was, so x is proportional to t power n, or x can be treated as some k times of t power n. So you have to do the velocity is equal to dx by dt, so which is given as k times of n into t power n minus 1, and acceleration is equal to dv by dt. So this is given as kn into n minus 1 into t power n minus 2. So this is the acceleration. Now actually you can calculate, so you can try to substitute these values here and then we will arrive at this relation. Got it? So find out the v square value, you will end up with the right side value. Got it? So note down one more. A point moves in a straight line so that its distance from a fixed point in that line is square root of the quadratic function of the time. Prove that its acceleration varies inversely. Prove that its acceleration varies inversely as the cube of the distance from the fixed point. Can you try to solve this? See this? So what he said was, a point moves in a straight line so that its distance from a fixed point in that line is square root of the quadratic function of the time. So the quadratic function of time is at square plus bt plus c is the quadratic function of time, and this one is equal to x square root of it. Now actually if you square on either side, this is x square is equal to at square plus 2bt plus c. Now if you take the derivative on either side with respect to t, then 2x into dx by dt is equal to, so 2at plus b. Now the acceleration is the derivative of dx by dt. That means, so this is, so 2 dx by dt is equal to 2at by x. Just a minute. You try to continue this and then actually try to solve it. So for simplicity, actually you imagine that this is 2b, so that actually you will get much more simpler way. Without this also you are going, without this also actually you are going to get the same answer. So for simplicity, you can imagine this, so that this 2 and 2 actually will cancel out. So what you are going to get is dx by dt is equal to at plus b by x. Here, if you take the derivative of this again, d square x by dt square is equal to x into d by dt of at plus b minus at plus b times of x dx by dt divided by x square. So this is d square x by dt square is equal to, so x times of d by dt of at is nothing but a minus at plus b times of dx by dt, which we have already calculated, at plus b by x. Divided by x square. So this you can further simplify it, xa minus at plus b by x. So here actually there is only one x is there. Now actually I will multiply with one more x here, and so that actually I can bring it out. So at plus b whole square divided by x square into x whole divided by x. Now here at plus b by x is nothing but, so that is the velocity square. So you note down this, I am going to erase it and then I will continue this. So Arun, so even if you put 2 or actually if you don't put, so it won't make any difference, but actually for simplicity, so to avoid these 2 we have put it. Yeah, so I think Vishal already got it. So after simplification, actually you are going to get inversely proportional to x cube. Got it? So this is how actually you can solve the problems. So So finally, I think so. This will come as d square x by dt square is equal to, so how much? AC minus b square. Yeah, AC minus b square divided by x cube, which essentially means that A is directly proportional to 1 by x cube. Got it? Note down one more. Prove that if a point moves with a velocity varying as any power, not less than unity. Of its distance from a fixed point which it is approaching. It will never reach that point. So can you try to prove this? Prove that if a point moves with a velocity varying as any power not less than unity of its distance, that means velocity is actually varying as the nth power of its distance from a fixed point which it is approaching. So it will never reach that point. That means suppose actually this is a fixed point on this particular straight line. Let us say a particle actually trying to move in this direction, and the velocity of this particular particle is nothing but v, which is proportional to x power n, where n is greater than or equal to 1. So this is the condition. So v is directly proportional to x power n, or v is equal to k times of x power n. Now actually he asked us to prove that this particle will try to reach this point, but it will never reach this point. Got it? Now actually the concept behind this is, so how can we prove that actually it will never reach this point? What is the reason behind that? Or what is the logic behind that actually? So how we can prove that it will never reach? No idea. So if you want to prove this kind of scenario, now actually we have got all the relations of the acceleration, velocity, displacement and time. Now this fixed point is nothing but x is equal to 0 for us. So it wanted to reach this particular fixed point, which is nothing but the origin. To reach from here to here, where this x is equal to 0, it will take a time of infinite. So at x is equal to 0, we have to prove that t is equal to infinite. So which essentially means that it will never reach. It will take infinite time to reach this particular point. So this is the logic behind this proving. Got it? Now you can try. So that's great. So but actually here we need to be considering two different aspects, n greater than or equal to 1. So we have to treat two different aspects. One is the case 1. We have to treat n is equal to 1. Why? Because n greater than or equal to 1, what he says is v is directly proportional to x power n. That means v is equal to k times of x power n. Now this n may be greater than or equal to 1. Now here, if n equal to 1, then this is dx by dt is equal to k into x power n, and dx by x power n is equal to k times of dt. Now in this differential equation, so if n is equal to 1, the integral will be different. If n is equal to greater than 1, then the integral will be different. That is the reason actually we have to divide this problem statement into two different parts. So case 1, n equal to 1. Now if you integrate it, dx by x is equal to k times of dt. Then if you integrate on either sides, log x is equal to kt plus some constant c. Now at x is equal to 0, this is going to take x is equal to 0. What is log 0? Infinite, right? So log 0 is minus infinite. So minus infinite, so that is kt plus c. So to reach this particular point, then actually it will take c minus infinite time. So this is again minus infinite. So this is the time taken. That means it will never reach. Now actually you take n greater than 1. Now if n greater than 1, then actually this integral is going to be, so x power minus n into dx is equal to k dt. Now again integrate it. So x power minus n, it implies, so x power minus n plus 1 divided by x power minus n plus 1, sorry, minus n plus 1. So this is equal to kt plus c. Now again, here also, this is x power minus n plus 1. So this is 1 by 1 minus n into 1 by x power 1 minus n. n minus 1. So this is equal to kt plus c. Now here actually if I take again x is equal to 0, x is coming in the denominator. Now 1 by 0 is again infinite. That means t is equal to infinite again. That means it will take whatever may be the form, n may be 1 or maybe greater than 1. So n greater than or equal to 1. So at x is equal to 0, t equal to infinite. Got it? So this is the scenario. So if it takes infinite time, which essentially means that it will never reach this particular point. Got it? So this is about the rectilinear motion, where actually we are dealing with instantaneous acceleration and instantaneous velocities. So in the next class actually I am going to deal with the constant acceleration. Some of the problems actually you know already the concepts, so you know already the basic formula. Now actually we are going to solve some of the problems based on the constant acceleration case. Got it? If you have any questions now, you can ask me now. Any questions? Yeah. Fine. Yeah, that's all. Thank you.